Silicon Photonics Explained, where we'll be talking about silicon nitride today, from telecoms to the quantum range. And if you're like me and you are interested in silicon photonics, I want you to, and you want to find out more, you don't want to miss out on the Silicon Photonics Summer School. This is the world-famous EpicsFab Summer School. It runs every year. It's been running for 8 years. This will be the 9th year, and it's right here in Southampton. So Cornerstone will be hosting it at the University of Southampton. There will be 20 experts in photonics, silicon photonics from around the world, talking about various topics from space to telecoms to quantum to medical applications, across the whole range. There'll also be dedicated networking events where you can talk to the experts directly about the topics that are relevant to you. And there'll be much more too. There'll be lab tours too and whatnot. So this will be running from the 24th to the 28th of June. So put that down in your diary here in Cornerstone in the University of Southampton. If you haven't already, spaces are limited, so I'd encourage you to avoid disappointment. Do register sooner rather than later. Well, I'm really excited about today's super cool talk. If you want to watch any of the previous episodes, they're on our YouTube channel. Just go to YouTube Cornerstone or Cornerstone Photonics. Just get the search terms right, or just scan this QR code. It'll take you straight there, and you can watch any of the previous episodes there. So this is Silicon Photonics Explained, where we're going through key silicon photonics technologies, all you need to know. In May, there will be a talk about how silicon photonics circuits are made. What are the fabrication processes behind this? And you'll find out firsthand how foundries operate and what fabrication processes are involved. In April, so just a few weeks from now, there will be a talk about mid-IR silicon photonics and how that's impacting the world from medical applications all the way to space. Today, you'll find out how silicon nitride is shaping the world we live in, from quantum applications to everyday telecoms and datacomms. Without further ado, allow me to introduce our fantastic guest on today's talk, Dr. Thalia Dominguez Bucio. Hi, Thalia. We're so pleased that you can join us today. So tell me, silicon nitride is a really hot topic. Why is that?
Well, that's the question that we want to answer today. I think it has been gaining a lot of popularity because of the properties that it has and the things that it can add onto silicon photonics platforms that are already traditional, and all the other things that you can do with it. So the whole idea of this webinar is for us to explore why silicon nitride is becoming popular and what we can do with it.
Super cool. I'm really interested in this talk.
Okay, so I'm going to share my screen then. As Ramsey mentioned, today the talk that we're going to go through this webinar is about how silicon nitride is shaping the world of photonics. And you will ask, if silicon photonics is already there, why would we need silicon nitride? So today, what I'm going to do in this talk is to guide you through the process of understanding why silicon nitride is becoming so popular. Why is it that silicon nitride photonics is becoming a thing? So we're going to start first by having a quick discussion about silicon photonics itself. Then we're going to talk about what are the advantages or what are the reasons that silicon nitride has been brought into the integrated photonic community. We're going to discuss some of the basic building blocks, and then we're going to go into diving in some of the applications that include low energy modulation, optical processing, microscopy and spectroscopy, and some quantum technologies. Let's start with the basics. I'm pretty sure that most of the people that are here in the webinar, they are familiar with silicon photonics, but just in case there's someone that is not very familiar, silicon photonics is a technology that is allowing us to fabricate complex photonic integrated circuits on a chip level that can not only transmit light, but that can process them. Now, the rationality behind silicon photonics is that it takes advantage of its CMOS compatibility. This is very important because it uses the standard CMOS processes that are already used to fabricate electronic devices, which means that we can fabricate silicon photonics devices in a large scale and at a very low cost. The other advantage that silicon photonics takes is the high index contrast that silicon has compared to the cladding material that we typically use with it, which is silicon dioxide. Because we have this high index contrast between both materials, we can fabricate devices that are very small and very compact. Now, being so, silicon photonics has opened a wide range of possibilities for a wide range of applications. It can be used for data center photonic integrated circuits. It can be used for environmental monitoring or chemical sensing in the mid-infrared. As you've seen in our previous webinar, it can also be used for beamforming and beam steering for their applications. It can also be used for programmable photonics or for medical diagnostics. So, if silicon photonics itself, just using silicon, we can make devices for all these applications. The question is, why would we want to use silicon nitride? Is there any reason? If we can do everything with silicon, why would we even bother bringing silicon nitride into the game? If silicon photonics can do so many things, why would we want to use silicon nitride? And in order to answer this question, we need to dive a little bit further into the properties of the material itself. So silicon is a semiconductor material, and it has many advantages. As I said, it has a high refractive index contrast that allows us making very small devices. It's transparent, so we can use it for telecom applications. But the same way it has so many advantages, it also has certain limitations, and these are all due to its intrinsic properties. So if we compare silicon and silicon nitride in terms of its intrinsic properties, we can see that there's a difference, and we can understand why silicon nitride might be a good candidate for integrated photonic circuits. So to start with, if we talk about the transparency, silicon itself, it's only transparent at wavelengths above 1.1 micron, which means that silicon can only be used for applications that require transmitting light in the near-infrared part of the spectrum all the way to the mid-infrared. Now, if we couple that to the fact that we typically use silicon with a silicon dioxide cladding, it limits the wavelength range in which we can use silicon to wavelengths between 1.1 microns and 4 microns, which is the longest wavelength at which silicon dioxide is transparent. Now, if we look at silicon nitride, silicon nitride on the contrary, it's transparent all the way to from the visible, let's say around 400 nanometers, almost dipping a little bit into the UV part of the spectrum, all the way to the mid-infrared up to 7 microns. So it covers a wider range of wavelengths. Then again, if we look at silicon itself, it's both silicon nitride and silicon possess nonlinear properties. They can be used for nonlinear applications because they have a nonlinear coefficient. In this case, chi3. The main difference between these two materials is that silicon possesses a significant photon absorption, which means that if you're doing a nonlinear processor, even a normal processing, which you're pumping a lot of power in your circuit, the power that you can handle in your waveguides is limited to only tens of milliwatts. Now, if we look into silicon nitride, this is not the case because the two-photon absorption is negligible. So even though the nonlinear coefficient is a bit lower, we might be able to get a nonlinear process that it's good enough for the application that we need because it's not so affected by the nonlinear absorption losses. Then, if we look at the index contrast, as I mentioned before, one of the advantages of silicon is that it has a higher refractive index contrast, which means that we can fabricate very small devices. Now, the problem with that is because it's a very high index contrast, the devices that we fabricate are going to be very sensitive to roughness. So every time we etch our waveguide, we will have some roughness in the sidewalls, and that will increase the losses of our waveguides. And on top of that, because the devices are so small and the refractive index is so high, if we have some fabrication error, then the response of our device is it can vary dramatically with respect to the target response because of these fabrication errors. When we look at silicon nitride, because it has a moderate refractive index contrast, in this case, it has a refractive index of 2.0 compared to 1.44 of the silicon dioxide, the difference is smaller. So what that means is that when we fabricate silicon nitride devices, these will be less sensitive to roughness, and then they will be also less sensitive to fabrication error. So there's chances that even if you fabricate a device and there's a big fabrication error, you might be able still to get a device that works within the constraints or the limits of your application. The other characteristic that silicon has is that it has a high thermal-optic coefficient, relatively. This is in the order of 10 to the minus 4K, which means that you can exploit thermal processes to tune devices. The problem is that it's very useful when you want to do a modulator, or like a thermal modulator, you want to do a switch. But if you have an application in which you're using, let's say, for example, a ring resonator, which is high quality, that it's very sensitive to temperature variations, you may not want silicon, because then any temperature fluctuation in the room where you are will change the response that you're perceiving from your device. On the contrary, silicon nitride has a thermal-optic coefficient which is 1 order of magnitude lower than that of silicon, which means that it has the potential to be less sensitive to temperature variations. And finally, and one of the most important properties that it's limiting silicon itself is that silicon, as we use it typically in the crystalline form, is fabricating in SOI wafers that are bonded. So it's very difficult to integrate this material with other materials themselves, unless you start doing other kind of deposition of silicon to get amorphous silicon or polycrystalline silicon that will inherently increase the losses of your devices, unless you do very complex processing techniques to try to reduce the losses. Silicon nitride, on the contrary, is very flexible. It has the potential to be integrated in multi-layer schemes. Yeah, so in a nutshell, these are some of the properties why silicon nitride might be seen as an alternative to silicon. What I mean as an alternative is it means that we don't want to replace silicon, because silicon is doing a lot of things very well on its own. It's more about extending the functionality of silicon to the areas in which it cannot perform using silicon nitride. And we're going to discuss more into detail now what are the advantages and what are some of the reasons why silicon nitride is becoming very popular. So I mentioned intrinsic properties of silicon nitride. Now let's talk about something that I haven't mentioned before. The other thing that makes silicon nitride very popular for integrated photonic devices is that it's a material that is CMOS compatible. What that means is that it's a material that's already in the production line. It's not something that we need to introduce into the CMOS manufacturing in the CMOS clean room. It's already there. It's been used for years in electronics. So what that means is that we can use the standard CMOS processing, or the standard CMOS processing techniques that have been developed during the electronic boom, and we can get wafer scale manufacturability of our silicon nitride devices. We can fabricate silicon nitride devices on 8-inch wafers, 12-inch wafers, compared to other materials that are also around in the integrated photonic community that can only be fabricated in very small wafers, which means overall that we can fabricate these devices at a low cost. When we talk about the CMOS processing, not every single silicon nitride layer is the same, and it depends a lot in the fabrication technique that is used to deposit the material. And there's quite a few, but the most popular ones that are standardly used to deposit silicon nitride layers are two. The first one is LPCVD silicon nitride, which is low pressure chemical vapor deposition silicon nitride. Then we have plasma enhanced chemical vapor deposition CVD, which will create the plasma enhanced chemical vapor deposition silicon nitride. Now, what's the difference between these techniques? And this is something that is very important to understand, because depending on the technique, the technique will determine some of the properties of the silicon nitride layers that we obtain, and that will determine for which applications each of these types of silicon nitride is more appropriate. In this case, if we talk about LPCVD silicon nitride, this silicon nitride is deposited in a furnace. In the furnace, we pump the gas, we heat it up at very high temperatures, and that's how we deposit our silicon nitride. Now, it's a high temperature process. What it means, it gives us a very high uniformity, and we have the potential of achieving extremely low losses in the order of less than 1 dB per centimeter. In some cases, there's been some demonstrations of LPCVD silicon nitride with losses down to 1 dB per meter. Now, the disadvantages of this process is that it's done at a very high temperature. Why would this be a problem? The problem is that if you, for any reason, you want to integrate your silicon nitride with other materials, such as silicon, and you have an active device that has doping, if you heat it up at high temperatures, you will affect detrimentally the performance of your active devices. The other problem that the LPCVD silicon nitride has is that it's because it's deposited in a furnace, high temperature, and you deposit on both sides of the wafer, you tend to get a very high stress. So typically speaking, you cannot deposit silicon nitride layers thicker than 600 nanometers. So you're limited to thickness of 600 nanometers unless you do some more complex fabrication processes. Now, if we go back to PCVD, on the contrary, what we see is that in the PCVD layers, we have a very low temperature. What we say it's a low temperature for CMOS fabrication processing is less than 450 degrees. The other thing is that the technique itself allows to deposit thicknesses greater than 600 nanometers. We fabricated waveguides up to 1 micron or 3 microns of silicon nitride, which means that because it's done at a low temperature and you can achieve very thick layers, you have a more flexibility in terms of the stack integration. So you can put it on top of other materials, you can integrate it with other materials on top, or you can integrate other materials on top of it as well. And the disadvantages of PCVD is that although it gives you very good stackability and very good properties for multi-layer integration, it still has lower losses than silicon in the terms that they are typically below 2 dB per centimeter, but they are not as low as the ones that you can achieve with LPCVD. And you just get a good uniformity, not as good as with LPCVD silicon nitride. The other thing that makes silicon nitride very attractive for photonic integrated circuits is that besides it being CMOS compatible and you can fabricate it with standard CMOS processing technology, is that you have certain flexibility that you don't have in silicon. In silicon, you will typically just deposit silicon crystalline silicon. You will get this crystalline silicon wafer, or you will deposit amorphous silicon, but it's more tricky to tune its properties. Whereas in silicon nitride, you can tune the optical properties of your material by changing the refractive index during the deposition process. So during the moment in which you're depositing your layers either by LPCVD silicon, LPCVD or PCVD, you can tune the gases to get a different composition of silicon nitride that will determine the refractive index, and this refractive index will determine the properties of your layer. So in this case, typically you can tune the refractive index of silicon nitride all the way down from, let's say, 1.7 in the refractive index all the way to 3. Now, when we get a composition that is close to 1.33 nitrogen and silicon bonds, we get a refractive index of close to 2.0, which is the standard stoichiometric silicon nitride. If we, on the contrary, we increase the silicon content of our layers, we will enter into a regime that we call the silicon-rich silicon nitride layers. And if we deposit less silicon and we increase the amount of nitrogen atoms that are incorporated in our layers, we will enter into the nitrogen-rich regime. Now, why is this important? Because each of these layers will have different optical properties. So if we talk about the stoichiometric silicon nitride, it tends to have very good losses in the near infrared. So typically when we talk about foundry services, this is the kind of silicon nitride that you use. It's the stoichiometric silicon nitride, which is deposited at high temperatures that has very low losses for the near infrared part of the spectrum. If you go to the other end in the silicon-rich regime, the advantage is because you're increasing the silicon content, you will have a high nonlinear coefficient, which makes this material very suitable for nonlinear applications such as all optical processing, all optical switching, and even some nonlinear processes requiring quantum photonics. Now, if we go to the lower part of the refractive index spectrum, we have nitrogen-rich layers, which have a wider band gap and a low autofluorescence. This is going to make a bit more sense in the next slide, but what it means is that this particular layer is more suitable for visible applications, for metrology, for microscopy, for spectroscopy, and also for quantum photonics. Now, as I mentioned, we can tune the composition of our silicon nitride layers all the way from nitrogen-rich to silicon-rich, and that will change the band gap of the material. And this band gap is related to the transparency window of the material. So if we look at the transparency window of typical integrated photonics materials, we will see that there are some materials that are transparent in the UV part of the spectrum. Some of them are transparent in the visible part of the spectrum, some of them in the near infrared, and some of them in mid-infrared. Now, if we look more into detail, silicon dioxide, as I mentioned before, is transparent all the way from the UV to 4 microns. Silicon, it's only transparent from above 1.1 micron all the way to 8 microns, give or take. Germanium is transparent from 2 microns all the way to the mid-infrared. And then you have silicon nitride, which is transparent from close to the UV part of the spectrum all the way to the mid-infrared. And then you have some other materials like aluminum oxide and tantalum pentoxide and aluminum nitride that have a wider transparency window. Now, this is very important because what it means is that silicon nitride itself can cover a wider range of spectrums compared to the standard silicon photonic platforms like germanium, silicon, and silicon dioxide because it's transparent all the way from the UV to the mini-infrared spectrum. And although it might not be as good in terms of the transparency window compared to aluminum nitride or tantalum pentoxide, it's one of the preferred materials because it's a material that it's very standard in the CMOS production line. And there's capability of fabricating at high volumes. Now, this opens a wide range of possibilities for silicon nitride because you can use it for applications in which you require near-infrared wavelengths, you can use it for the mid-infrared, you can use it for the visible, or you can use it for applications in which you will cover all these wavelengths. Yeah. Because the material is transparent, both in the near-infrared and the visible, that means that we can achieve low propagation loss. If we look, again, as I mentioned before, there's two different types of losses. We have the LPCVD losses and the PCVD losses. This is important because one material will have ultra low losses and the other one won't. So when we talk about LPCVD waveguides, we see that the losses are very low. They are there's less than 1 dB per centimeter. But it all will depend on the geometry that you have. If you have a geometry that has high confinement or a low confinement. Typically speaking, when we talk about LPCVD waveguides, the lower losses are achieved when you have a low confinement waveguide. What do I mean with this? I mean a waveguide that is made with a very thin layer of silicon nitride and a very wide core, which means that most of the mode is actually traveling in the cladding. In that way, you can reduce the losses from the roughness on the sidewalls, and you can lower the losses that you're seeing in your waveguide all to levels of 1 dB per meter. Now, once you go to the moderate kind of confinement, which is around 40 to 80% of the mode confined within your waveguide, we're talking about silicon nitride thicknesses are in the order of 300 nanometers, which is one of the standard silicon nitride technologies. You will see that the losses increase all the way to ranges between 1 dB and between 1 dB and 0 dBs, but they are much higher. If we were going then for high confinement waveguides in which we have thicker cores, which, as I mentioned, it's very hard to achieve with LPCVD because it's limited because of the stress, you will typically expect the losses to be higher. However, in recent years, there's been a lot of work going into trying to achieve these high confinement LPCVD waveguides with thicker layers using more complex fabrication process than the standard LPCVD. You have waveguides that can have losses below 0.05 dB per centimeter using processes like the Damascene process and multi-step annealing. You can do a technique that is called twist and growing, which basically you grow the half of your thickness of your layer and then you twist it again, and also doing some sort of cycling. And that's how you can achieve these ultra low losses in high confinement waveguides and in low confinement waveguides using LPCVD silicon nitride. Now, if we move to PCVD, the losses look completely different. Now we're talking about losses in the order of let's say 1 dB per centimeter all the way to 6 dB per centimeter, give or take, depending on the confinement factor of your waveguide again, and in the process, in the technique or the recipe you're using to deposit your layers, because they are not on a high temperature. Each of these layers will have more hydrogen hydrogen content, and that will impact the losses of your waveguide at 50 nanometers. But give or take, in terms of moderate confinement waveguides, high confinement waveguides, you can see losses between the 6 dB per centimeter and the 2 dB per centimeter, which in some cases, if we're talking about 2 dB per centimeters, that might be better the losses that you can achieve with silicon. Now, if we move now to the visible part of the spectrum, we will see that we can also achieve low loss waveguides. So in this case, if we go covering all the wavelength range from 400 nanometers, 450 to, let's say, 900 or 1000 nanometers, we will see that we can achieve losses in the order of less than 5 dB per centimeter. So if we start first, some of the first demonstrations were done using layers of 100 nanometers to cover all these wavelengths, and with these layers, it was possible to achieve losses below 6 dB per centimeter at the lowest part of the spectrum, and then reduce the losses all the way to less than 1 dB per centimeter in the longer part of the spectrum. However, in order to increase or To reduce the losses that you achieve with these waveguides, what you need to do is actually go into a low confinement waveguide regime. So if you reduce the thickness of your layer from 100 nanometers down to 20 or 20 nanometers, it is possible to reduce the losses all to levels below 0.05 per centimeter in the whole wavelength range, covering 450 nanometers to, let's say, 900 nanometers. But these are not the standard layers that are available in foundries. If you just talk about foundry fabrication layers, typically they will have losses in the order of 1 dB per centimeter all the way to 6 dB per centimeter. So here I have two examples of waveguides in the visible. So these ones were fabricated in standard foundry services with thicknesses of 150 nanometers. And you can see that you can transmit the light very well, but you see some scattering. And of course, you see some losses because the light is not so intense. However, if you look at these low loss waveguides, which are fabricated with a thinner silicon nitride core, you will see that you can get very long spirals with a very good transmission of the light in at 450 nanometers, which is the shorter part of the spectrum, and almost at 700 nanometers, which is the red part of the spectrum. Yeah. So far we have talked about the optical the fabrication of the silicon nitride layers, how we can tune the refractive index, how these affect the losses, and how we can achieve low losses both the near infrared and the visible part of the spectrum. But one of the key properties of silicon nitride is that it also exhibits nonlinearity. Now, how does this nonlinearity relates to the refractive index of the layers? So if we look at this plot here, in which we have the refractive index against the nonlinear coefficient, we can see that we have the silicon dioxide here, that is in the lower part of the spectrum, and then we have the amorphous silicon and the crystalline silicon, which have a higher nonlinearity. So in this case, when we have the silicon layers, we have two photon absorption, and in the lower part of the spectrum, we have no photon absorption. So this is important because that means that if we start increasing our silicon content, the silicon content in our silicon nitride layers, we can start seeing a higher nonlinear coefficient, which might get a more efficient process, all the way to the point that we get ultra silicon-rich nitride layers, silicon-rich silicon nitride layers with a refractive index of 3, which makes them very useful for all optical processing applications. The other thing, as I mentioned, is that it's less sensitive to temperature variations. So we look here at this is the responsible standard silicon ring resonator. You will see that if we change the temperature from 20 to 60 degrees, the shift of the central wavelength is quite big. If we do the same with silicon nitride, you will see that the change is much smaller. So we're seeing that the sensitivity of silicon is around 8 picometers per degree centigrade compared to silicon nitride that only has 19 picometers per degree centigrade, which means that silicon nitride is more stable to temperature variations. Now, by exploiting all these possibilities, all these properties of silicon nitride, it is possible to fabricate waveguides, nonlinear waveguides, and most of the basic passive silicon nitride building, silicon photonics building blocks. We have waveguides, we have bends, we can get into double couplers like edge couplers or rhythm couplers. We have splitters, and we have other filter and resonators such as array waveguide grating, silicon nitride resonators, and we have Mach-Zehnder interferometers. But you need to bear in mind something. Here I'm just mentioning passive devices. That's one of the caveats of silicon nitride. That although it's very good for many things, it can only be useful for fabricating passive devices. So if we wanted to do some active functionalities to the silicon nitride layers, we need to integrate these silicon nitride layers with other materials. We can achieve modulation by integrating our nitride with silicon germanium stacks, optic polymers, lithium novad, BTO, transition metallic chalcogenides, and transparent conductive oxides. We can also create some non-volatile devices by adding phase change materials, or we can integrate lasers and detectors by incorporating our silicon nitride with 5 materials. Typically, the standard silicon nitride fabrication process goes very straightforward. We start with a silicon dioxide layer, then we deposit our silicon nitride with either technique. We do the lithography, we etch the waveguides, and then we cap it. Or then sometimes we will even open the cladding in order to get some sensing possibilities. Under this context, Cornerstone itself offers the silicon nitride platform, the standard silicon nitride platform, which is 300 nanometers of silicon nitride, and it's fully etched. And with this material, we're getting losses around 0.5 dB per centimeter, and we have grating couplers with less than 10 dB per grating. So using the standard silicon nitride or using silicon nitride for photonic integrated circuits open the possibility of using the material of photonic integrated for a wide range of applications. We have telecom, data centers, and LiDAR. So you can use it for augmented reality, for biosensing, for microscopy and spectroscopy, and for quantum technologies. And right now, what I'm going to do is I'm just going to skim through some of the applications so you can get an idea of what can be done. So to start with, I'm going to discuss a little bit about low energy modulation. So in this case, when we talk about low energy modulation, we are talking about integrating modulators that can consume very low energy in our silicon nitride. And as I mentioned before, silicon nitride cannot, with silicon nitride itself, you cannot do active devices. So what you have to do is actually integrate it with a material that can achieve this modulation. So in this case, one of the applications is to integrate silicon nitride to be able to achieve electroabsorption modulators in the O-band by integrating the silicon nitride layers with multi-quantum weld stacks of silicon germanium. Typically speaking, this has been done at 1550 nanometers, but in the O-band it's a bit more tricky because the multi-quantum welds that can work at this wavelength tend to be very thick. So if you wanted to integrate it, what you will have to do is actually etch your silicon, which is around 1 micron thick, and then you will have to grow this multi-quantum weld of silicon germanium layers, and then create your devices. The problem is that if you do it this way, then you end up with defects that make the transitions not harder, but they are not as smooth as they could be. So in this case, one of the things that you can do with silicon nitride is instead of trying to grow the multi-quantum weld on top of the silicon nitride, what you can do is actually start with a planar multi-quantum weld stack, then etch the multi-quantum weld stack, and then deposit your nitride. Because if you do it that way, you get a smooth transition between the two materials. So in this case, to achieve this, you will have to etch your multi-quantum weld stack, deposit an anti-reflective coating, then you can deposit the silicon nitride, and then you can etch the nitride and planarize it, and then you can etch your waveguides in both materials. In such a way, it is possible to achieve the integration of silicon germanium multi-quantum weld waveguides it's smoothly and simply integrated with silicon nitride waveguides. And if we do the metallization necessary to create a electro-optic modulator, it is possible to achieve modulation, high-speed modulation in the order of 65 GBs per second and 82 gigabit per second, with extinction ratios between 2 and 3 dBs, and with energy consumption of less than 70 femtojoules per bit. So this is one of the things that you can do. Now, the other area in which you can use silicon nitride is for all optical processing. And you will ask me, what is all optical processing? All optical processing encompasses all the processes that you can do exploiting the nonlinearities of the waveguide. So in this case, most of these processes are done using standard stoichiometric silicon nitride or silicon-rich silicon nitride. So one of these examples is what we call parametric wavelength conversion. How does this work? So we start with a nonlinear waveguide. And typically you would put two signals into your waveguide, let it pass through your nonlinear waveguide, increase the power, and then with this increased power, you will start generating this nonlinear process that will generate two extra wavelengths, which is called the four-way mixing process. So in this case, if you wanted to do something, you could put a signal close to 1515, you could use a pump close to 1515, and then by tuning your signal, you will be able to generate new signals called the idlers at shorter and longer wavelengths. And why this is useful? The reason why this is useful is because by exploiting this wavelength conversion, you can increase the aggregate of wavelengths that you can transmit in telecom and datacom, and start exploiting other wavelength bands that haven't been exploited so much because we don't have the lasers, but there's low loss fibers that can transmit this wavelength, like in the 1600 regime. Now, similar to this parametric wavelength conversion, we have also another aspect of it, which is the intermodal wavelength conversion. In this case, instead of using, we do a similar process. We have two pumps. We have a signal and we'll generate two idlers. But in this case, instead of matching the fundamental mode of the pump to the fundamental mode of the signal, we will use our two pumps in the fundamental mode, and we're going to match the mode of these two pumps, fundamental mode, to the second order mode of our signal and the idler that we will generate. So in this case, we're maximizing the T00 mode with the T10 mode at the different wavelengths. In this case, it's 1515, close to 1515, and 1600. The advantage of doing this is that if we have a multi-mode waveguide, we can support multiple modes in which we can do this phase matching condition, so that we can extend the wavelength that we're generating to much longer wavelengths. Besides, using the intermodal wavelength conversion, what we see is that compared to the intermodal wavelength conversion, which is what I mentioned in the first slide about this all optical processing, we see that when we started tuning the pump, so we're trying to move our signal and the islands that we're generating further away from our pump, what we see is that the four-way mixing efficiency starts deteriorating because the process starts being not phase matched. Whereas when we have this intermodal process, we see that even if we tune the pump up to 30 nanometers, the process is still phase matched. So that means that we can move our idler generated to much longer wavelengths. And by using this kind of a scheme, it is possible to demonstrate modulation like quadrature amplitude modulated signals that start at 1550 nanometers, and then they are converted in our nonlinear waveguide to wavelengths close to longer wavelengths, all the way to 1600 nanometers. Both applications that I've just discussed now, the low energy modulation and the all optical processing, are done in the infrared part spectrum, meaning 1310 nanometers, 1550 nanometers, which are wavelengths in which silicon could also perform. However, one of the advantages of silicon nitride is that it can also work well for visible wavelengths, and that's where other applications come in. The first one that I want to discuss today is microscopy and spectroscopy. So when we talk about microscopy, we're talking mostly about the techniques that are used to analyze biological samples. And typically speaking, when we talk about these applications, what happens is that you need, in order to analyze what's happening with samples, you need to stimulate with the laser certain fluorescent markers in some microscopy techniques, like fluorescence microscopy, or in optical coherence, or not optical coherence tomography, but in I forgot the name, in other techniques. Not only fluorescence microscopy, but you have optogenetics as well. So typically speaking, what you need in order to be able to perform these techniques very well is to have a source, a multicolor laser engine, basically multiple lasers that can be combined in one fiber, so that you can stimulate your sample with all these wavelengths at the same time. Now, the problem with this is that, typically speaking, when we talk about the measurements that are done in the lab, these setups tend to be very big. They need electroacoustic modulators, they need mirrors, they need switches, and they need the fiber racks and all these kind of things. So they are very big. So it's very difficult to make a compact device. However, if we were to use silicon nitride to miniaturize the component of this multicolor laser engine, we will be able to create an engine that is more compact, and that also allows us to modulate the signal that is sometimes important in these microscopy techniques, and also control in certain way the power that we're getting into our fibers. So in this particular application, what can be done is you get your laser diodes, and you interface them with a small optical system into your chip, and then you have these Mach Zehnder interferometer switches that will be used to take each of these wavelengths and split them into two different outputs. And then, because it's a switch, you can modulate when you turn on and off each of these wavelengths. Then each of these wavelengths will be combined with these splitter combiners in a way that by the end, when you get to the edge coupler that goes into the fiber, you will have all the four colors traveling at the same time in the same waveguide, so that you can couple it into the fiber and you will have four colors at the same time. Something similar to this. So you have your laser engine here, you have the different colors individually with your laser diodes, and then you have an output in which you have all the wavelengths together, which is something that you wouldn't be able to do with silicon, because silicon is not transparent in the visible part of the spectrum. Lastly, but not least, the last application that I want to discuss with you today is quantum technology, because it's very vibrant and it's a very hot topic. So one of the ideas of using integrated photonic circuits lies in the realm of quantum information processing. So in this case, the whole idea is to be able to generate a multi-chip or an on-chip quantum processor that will normally require having a single photon source, meaning a source that can generate undistinguishable and high quality single photons, one photon at a time, that will be interfaced with very low losses into a photonic integrated circuit that will do all the processing of these photons that are being generated, and then have as an element that will be able to detect what is happening with these photons. In this case, it's with superconducting nanowire photodetectors. So what will happen in this system, for example, in the one that I have here in the image, is that you will excite with a wavelength. In this case, I think it's 950 nanometers. You will excite your single photon source that will start generating single photons, a stream of single photons deterministically, that then will be interfaced into our system here that has an electro-optic modulator and some polarization beam splitters in order to couple this stream of photons into our programmable photonic integrated circuit. Once the programming or the operation is done on the bits, then it can be detected in this array of single photon detectors. Now, where does silicon nitride come from? These devices could be done on silicon. However, they can also be implemented using single photon sources using silicon nitride waveguides and using programmable photonic integrated circuits in silicon nitride. Now, most of these circuits, the programmable circuits, are driven thermally. And as I mentioned before, silicon nitride is not the best in terms of the thermo-optic coefficient. However, it's possible to design heaters that will allow you to heat enough silicon nitride to achieve the active functionality as well. How do we generate then this single photon source, which is one of the most critical elements for this quantum processors? So there's multiple ways, but typically speaking, you want to integrate your waveguide, your standard integrated photonic waveguide, with a material that is a good single photon source, which is technically a bulk material, like semiconductor material, like quantum dots from 3-5 materials, or nanodiamonds. So in this case, what you can do is get a silicon nitride waveguide that is buried, and then you create some sort of hole in which you're going to integrate this 3-5 semiconductor single photon source. In this case, it's done with gallium arsenide. And what you do is that then you pump your light, and these gallium arsenide quantum dots will start generating these photons. And by creating this mode transformer, you can transfer this mode, these photons that are being generated by the single photon source, into our silicon nitride waveguide, and then we'll interface with the rest of the elements. And finally, the other application that can be used, that in which silicon nitride is gaining popularity, is in the realm of atom and ion quantum technologies, because it can be used for atom cooling and clocking. So there's a variety of applications like atomic clocks, quantum microscopy, or even quantum computers, ion-trap quantum computers, in which it's necessary to control precisely. In order to be able to control precisely all the atoms that you have in your system, you need to have a multiple wavelengths in order to be able to trap this atom, and not only trap it, also cool it, control it, and probe it. So in this case, when they are in, there's already implementation to this kind of system that literally take the whole room, because you have tables full of lasers and all the cooling systems and all the elements that are required in order to be able to trap these ions. However, if you were able to put all these elements in an integrated form using silicon nitride, you could have your lasers incorporated into very high quality resonators in order to be able to tune the wavelengths to the specific wavelengths that these atoms are sensitive to, and you will be able to then transmit it into some grating couplers, similar to grating couplers that will act as beamforming elements, and they can be used to trap your atoms and probe them and cool them at the same time. So I think that's pretty much it. Any questions?
Thank you so much. That was a fantastic talk. I really enjoyed it. Yeah, thank you so much. Our next talk will be on mid-IR, so mid-IR silicon photonics, on the 19th of April 2 p.m. GMT. And the reason I say GMT, check your calendars, because there'll be a change in the clocks, I think, between now and then. But just put it, if you sign up now and add it into your calendar should automatically update it anyway. And in this talk, you'll find out how silicon photonics is being used in the mid-IR range and how it's implemented in areas from medical all the way to space. So make sure you sign up to that today, so you can so straight into your calendars. So just here, check again if there's any more final questions. But yeah, I thank you so much, Thalia, for that fantastic talk. And we kind of look forward to the next session talks as well. And for everybody, thank you for your questions. These are really super cool questions and get us all thinking about things. Also, this talk will be available on YouTube if you're wanting to go back to some of those slides and kind of there was some good kind of really detailed information there that you want to look at in detail. It'll be on YouTube in the next week or so. So do check out and keep an eye on our Cornerstone YouTube channel. Thank you again, Thalia. Thank you, everybody. And we'll see you again soon in a few weeks' time for the next talk. Thank you and goodbye.